So we were studying the joint and the marginal distribution functions. And as we have done in all previous chapters, we are covering this chapter as well in terms of discrete random variables first, then continuous random variables second. So we have solved the question, and in this question, we were given a joint probability mass function that represents the joint probabilities of two random variables at the same time, x and y. And x was supposed to take the values of 1, 2, and 3, and y, random variable y, is taking values of 0, 2, and 4. And the joint probabilities are tabulated in this table. Now, we have summarized that the row sums of this table will give you the probability mass function of x, which is called the marginal probability mass function of x, and the column sums will give you the marginal probability mass function of y. So by using these marginal probability mass functions, we can in fact calculate the expected value of x or variance of x. Similarly, we can calculate the expected value of y and variance of y. So this means what? Basically, a joint probability mass function, or in other words, a joint distribution, gives you a lot of information related on marginal distributions, but not just the marginal distributions, it also gives you information on the dependence structure between these two random variables. Now we are going to cover that dependence structure in the following hours. So let's just solve the second question. This is the point where we have left. Now, we have an experiment where we randomly select two balls from an urn, and that urn contains 2 red, 3 green, and 4 blue balls. So in the total, by the way, my friends, if you have any connection problems, if you having a hard time hearing me, or if the screen freezes, please warn me on that by turning your microphone on. Every once in a while, I'm going to ask you if you can hear me or not. Now, let's just continue the question. We have 9 balls in total. 2 of them are red, 3 of them are green, and 4 of them are blue. And we are randomly selecting 2 balls from that urn. Okay, so we have an experiment where we select 2 balls out of 9. Now, in this selection process, we let x and y denote respectively the number of red and green balls chosen. Now, x is the number of red balls that are chosen in these 2 balls, and y is the number of green balls selected in these 2 balls. So what are the possible values of x and y? So the number of red balls that I am going to select in these 2 balls can be 0, 1, or 2. Similarly, the number of green balls that I'm going to select in these 2 balls can be 0, 1, and 2. But for example, can x and y be equal to 2 at the same time? Actually, it is impossible because in total we are selecting 2 balls. The number of red balls and number of green balls that are selected can at most be, the summation can at most be equal to 2. For example, I can select 1 green and 1 red ball, and here's the probability of that. So what is the probability of selecting a red ball and a green ball, which means the probability of x being equal to 1 and y being equal to 1, 2 at the same time? Now, we can define the sample space of this experiment with 9 choose 2 possible outcomes, if you remember from chapter 1. If you do not remember this from chapter 1, you can check page 39 for that, for the first chapter. And out of these outcomes, 9 choose 2 possible outcomes of this experiment, in how many of them we have exactly 1 red and 1 green ball? So this means what is the probability of selecting 1 red and 1 green? So this means 2 choose 1 times 3 choose 1 times 4 choose 0. So you need to choose 0 blue balls, 1 green ball out of 3, and 1 red ball out of 2. Now, this ratio is 6/36, and that probability is the joint probability of x being equal to 1 and y being equal to 1. So this is the joint probability mass value of x and y at 1, 1. Now, this is only just one case. Now, at part A, question asks us, write down and tabulate the joint probability mass function of X and Y. Now, we know that this is just one possible case. What are the other cases? Now, for example, we can select two red balls. When we select these two balls, we can possibly select two of the red balls. In that case, we will have the joint probability mass value of X being equal to 2 and Y being equal to 0. And in the numerator, in that case, we are going to write 2 choose 2, 3 choose 0, and 4 choose 0. That is going to simply make 1. Okay, that numerator is simply going to be equal to 1, and the probability is going to be 1 over 36. Another case is where we select two green balls, which is the probability of X being equal to 0 and Y being equal to 2. And in that case, in the numerator, we will write 2 choose 0, 3 choose 2, and 4 choose 0. Another case is where the number of red balls is equal to 1 and number of green balls is equal to 0, which means the other ball that we select is blue, and that is going to have 2 choose 1, 3 choose 0, and 4 choose 1 in the numerator. Another case can be where we select one green ball and 0 red balls. And in that case, this means we are selecting one green and one blue ball. And in the numerator, we write 2 choose 0, 3 choose 1, and 4 choose 1, so on and so forth. So these are the possible cases. Actually, we may select no red or no green balls. So this means these two balls that are selected are from blue balls. And in that case, we write 2 choose 0, 3 choose 0, and 4 choose 2 in the numerator. And that has a probability of 6 over 36. Now, we have 6 possible cases for X and Y to take values. Both of them can be 0. X can be 0 and Y can be 1. X can be 0 and Y can be 2. X can be 1 and Y can be 0. X can be 1 and Y can be 1. And X can be 2 and Y can be 0. Now, the probabilities that are calculated with the formulation given here, by changing the values, of course, are written here. So this is the closed form probability mass function that we should write for X and Y. So this is a joint probability mass function. It is giving us the probability mass values for the joint combination of the possible values of X and Y can take. And this is the tabulated format. This is the table format. So we know that both X and Y random variables can take possibly the values of 0, 1, and 2. And in the cells of this table, we are writing the joint probability mass values. And of course, because of the elsewhere condition here, it is impossible for X to be equal to 1 and Y to be equal to 2 at the same time, or vice versa, or they cannot be equal to 2 at the same time. So these three probabilities are simply 0. Now, the second part and the third part of this question is asking the marginal probability mass function of X and marginal probability mass function of Y. So what are we doing for those? Remember now, if we write the tabulated format for the joint probability mass function, if X values are shown in the rows, then the row sums here are going to give us the marginal probability mass values for X. For example, what is the probability of X being equal to 1? So we are basically summing up the joint probability mass values while X is equal to 1 and Y is taking different possible values that it can take. And summation done over Y is giving us the marginal probability mass value of X at 1. So we can do the same for 0 and 2 as in this case. And we are calculating the marginal probability mass function of X, where it takes 0 value with 21 over 36 probability, 1 value with 14 over 36 probability, and 2 value with 1 over 36 probability. Now, similarly, the marginal probability mass function of Y can be calculated by taking the column sums. So we are basically fixing the possible values of Y, for example, to 0, and the probability of Y to be equal to 0 is calculated by summing the joint probability mass values over changing values of x. So for the marginal probability mass for y at 0, we are summing these values up in this column, and that makes a 15 over 36. And respective marginal probabilities of y being equal to 1 and 2 are 18 over 36 and 3 over 36. Now, one thing you should be careful about, my friends, if you are calculating the marginal probability mass function of x, remember now you are running your summation over the y variable, okay? Similarly, if you are calculating the marginal probability mass function of y, you are running your summation over the other variable, okay? Do not forget about that. Now, finally, at part D and E, it asks calculate the expected number of red balls that are selected. So which is basically asking the expected value of x. What is expectation of x? The expected number of red balls selected is expectation of x. And in part E, it asks the expected number of green balls selected. It basically is asking the expected value of y. So since we have computed the marginal probability mass function of x, and the marginal probability mass function of y in parts B and C, in part D, we can compute the expected value of x by multiplying the possible values of x with the marginal probability mass values, respectively, and sum them up. And that gives us a 0.444. So when you select 2 random balls from these 9 balls, the expected number of red balls in these 2 balls is going to be 0.444, according to this calculation. Similarly, the expected value of y can be computed through the marginal probability mass function of y. So we multiply the possible values of y with the respective marginal probability mass values and sum them up. And that gives us the expected value of number of green balls selected. And that makes a 0.666, which is 2 over 3, basically. Now, I am just going to ask you a final question. What is the expected number of blue balls selected? Now, of course, if we have 2 red balls and the expected number of red balls is 0.444, if we have 3 green balls in the urn and the expected number of green balls selected is 0.666, obviously the expected number of blue balls that are selected is going to be 0.888, because there are 4 blue balls. Actually, we could have answered these questions very easily, expected value of x and expected value of y. Why? Because I know that 2 out of 9 balls are red. So if I select one ball randomly, then the expected number of red balls in that selection is going to be 2 over 9, okay? Just like a Bernoulli experiment. Imagine the expected value of a Bernoulli distribution. So you have the success probability of 2 over 9 and failure probability of 7 over 9. And the expected value of that Bernoulli random variable is 2 over 9. So if you select a single ball, then the expected number of red balls in that ball is going to be 2 over 9. So if you select 2 balls, not just one, but 2 balls, then again, by the proportionality, it is going to be 2 times 2 over 9, which is going to be 4 over 9, and 4 over 9 is equal to 0.444. So basically, I have 2, 3, and 4 balls in each color. And if I select 2 balls, in that 2 balls, the expected number from each color should be proportional to 2, 3, and 4, and their summation should give us 2. So 0.444, 0.666, and 0.888. If you sum these 3 values up, you will get 2. So that's the story of this question.